Good evening and welcome to this evening's webinar, Problems Worth Coding. I'm Brian Lannon and I am your host for this evening. Before I hand over to your super presenters, Jim Lowe and Peter Fox, I have actually seen some of this material before that these presenters have done at conferences, and I can tell you it's very good ideas and you are set for an action-packed evening. We are hoping that you may have already explored some of the 10 minutes of code activities and looking for what to do next. Your presenters are Jim Lowe, who is a research associate from the University of Technology in Queensland, and Jim's expertise is, well, in many things, but I have been particularly impressed by some of the data logging that he showed me, and yes, I was with him at Dreamworld where he threw us around roller coasters and the like wearing data loggers. That was a heap of fun. Peter Fox is a teacher of great experience, now working with Texas Instruments, and an absolute gun on the coding, and has some great problems for us to look at. And so without further ado, Peter, are you there, Peter?
I think I am.
I will hand the show over to you.
Thank you, Brian. Now, I know on the original introduction there, it talks about a Goldbach conjecture. Unfortunately, it was spelt wrong. I missed a D out of that one. I fixed that, though. It now has the D in it. But before I kick off, I just wanted to show people that we do have a section to step people through on our website. If you go into the teachers section on our Australian website, you'll see there's an option for TI code. So whether you're using an 84 or an nspire, then you can code through a series of lessons, each one designed to take about 10 minutes, hence its reference to 10 minutes of coding. And some of those represent a good precursor for the activities that we have on our website for TI coding. You'll see them in the STEM section of the Australian-inspired curriculum. And most of them translate pretty much straight across to an 84, because what we're really about is actually some basic coding, literally, some basic coding instructions, simple statements like if, then, and in some platforms it's called print, other ones it's called display. So there's only slight variations between what is output to a screen. So, well worth a visit, 10 minutes of codes. And I noticed in the lineup for the people attending this webinar, I have some from the US. I was over there doing a presentation that included some of this content. So it may be familiar to some of our participants. So I will temporarily visit this Goldbach conjecture. You'll see it gets a one-chip reference from me, saying that it's fairly easy. You'll have a bit of a chuckle when you see how easy that is to code. So let's go there. So the conjecture basically said every even number greater than 2 can be written as a sum of 2 primes. The original conjecture was that every even number including 2, but 1 was considered prime at the time. So there's a really cool command on the calculator that basically says, is this thing prime, yes or no? So it's a really simple program. So we'd start at, let's say, 1 and finish when we get to our number. This is our, like a little flow chart. We want to check, and I love this one, is I prime? And if not, then I haven't found a solution. If I is prime, even better grammar, then I need to check, is n minus 1 prime? And if n minus 1 is prime, then I've found a pair of solutions. That's basically the code. And in writing, here it is here. So simply we would request a number. That means we'd input a number, and the program will start a loop, and it will start, I've started it at 2, because there was no point starting at 1, because 1's not prime. And you can see from the code, it just says, if the current number is prime, and n minus the current number is prime, then display the 2 results. That's the end of the program. Now, Jim's probably panicking in the moment thinking, oh, does that mean it's my turn? No, because I figured that program was probably a little bit short for the people that are joining us on our webinar this evening. And you can make slight modifications. For example, you can actually make the for loop go through a bit quicker, starting at 3, and that way the only number that we won't run the program for is 4, because there's no point checking any even numbers. So that would say, oh, it's 3 to start off with, and then it's going to be 5 because it's stepping in lots of 2 according to the 2 just over here on the screen. So it makes it a little bit quicker, but not essential for students to do. So we can get students to explore a range of things, and that's one of the other items that I want to draw attention to this evening, is that a lot of the content that Jim and I are presenting tonight, it is a good solid mixture of mathematics and coding. It's not just doing problems for the sake of coding. These are good mathematical investigations for students to pursue. Now, don't be scared off because I've given this 3 TI chips. It just means that it includes some list stuff. So we'll see. So here's our problem statement. It says 2 points are placed randomly inside a 1 centimetre by 1 centimetre square. For our US visitors, you are welcome to type in 1 inch by 1 inch. It's irrelevant. What is the average distance between these 2 points? Now, it's worthwhile if you're using Navigator to give a quick poll and have the students think about it. A lot of students that I've found tend to type in a half, but they need to think of diagonals, in which case maybe root 2 would be the longest length, so maybe it's a half of root 2. That would be true if it was a circle. But at least we're starting to get a sense of where our answer might lie. It's probably bigger than a half, but probably less than 0.7. So we have an expectation of what that distance might be, that average. But for those of you that are going to sit down and do it using calculus now, it's a quadruple integral. You're probably there for a day or two working it out. So let's try using a code to solve the problem. So here's where we start our first bit of code. You can just watch. You can try and follow along if you're using your software. That might be a bit tricky. So the first thing we need to know is, how do I put some code in? If you're using the latest operating system, you'll see that we can go straight to the program editor here. If you're using an older version of the Inspire software, you'd add a calculator application and then put the program in.
That's operating system 4.4, I believe, Peter.
Yes, that's correct. So I'm going to make this a really creative title. How long? And that's the name of my program, so I've already started coding. It just doesn't do anything. A town on the Murray River in New South Wales, Peter. What was that, sorry? It's the name of a town on the Murray River in New South Wales. Oh, yes. Yeah, there's a lot of other weird towns up there too, like Wagga Wagga. All right, so let's start. We want to generate some random numbers. So if I'm thinking, if these were plotted on a Cartesian plane, which is one of the simulations, because this is an activity on our website, I might do rand and oops, I don't want a 0 in there. Conveniently, the random command, when I type it in like that, will generate a number between 0 and 1. If I wanted to generate a larger number, change to a 2 by 1 or something like that, then you can put coefficients in front of here. So I'll do these ones first. So this is my first point. Now, if you're wondering where you get the random command, it is in the probability menu. You can get it from the catalog. I'm using a computer, so I'm going to type it in. We're constrained for time here. So obviously I'll put my second point in. And I might want to calculate the distance. Now, I can do the calculation here, but it's not really going to do anything. I need to store it somewhere. So I'm going to store it in D. And I don't think it's rocket science. I don't think I'm scaring anyone off here when I type in that. Now, you can also, if you really want to, do subscripts here. There is a subscript tool. I'm just being lazy and not using it because I'm interested in getting the code out. Always much quicker on a keyboard than handheld, isn't it? Yes, it is. Yeah. So, I think most people will be able to figure out what that first bit of code is doing. Now the first thing well, not the first thing, but one of the things you might have noticed, as soon as I started typing, there's a little asterisk appears up here. So, Control B. B for compile. Does that make sense? No. But that's effectively what it's doing. It's not just saving it. It actually runs through. So when I make a mistake, which I probably will, it will tell me that there's a problem with it. So now I want to see where is that program and where can I access it from. So I'm just going to insert, I'll do it from here. Insert the calculator application and press the variable key, and there's my program. Now people might not have noticed, but there's a different little icon next to these things. The 0, 1, the binary sort of thing is for a program. Press enter and it's done. That was very exciting. But it's added a whole lot of variables onto my calculator here. You can see this one here. These are just numerical values. So the distance was 0.32. So what's missing here is to display. And I could put some text here. Distance. Put a comma. Put a D there. Press Control B again. No typos. That's good. Now if I go back and run my program again, this time it displays the distance. And I can just start pressing enter. That's probably a little bit quicker than the students calculating it, but no different than what they could have done in a spreadsheet. So what if I wanted to start recording the distances or doing lots of them? So we're going back to our program. Let's suppose I wanted, say, 10 distances generated. Then we put a loop in here for I is 1 to 10. I love that grammar. I is, there's 1 to 10.
I
and
is, you is,
yep,
we all
it.
is.
That's right. Math teachers were okay. And we need to end the for. Now, if you're worried about these sorts of commands, like how do I know I've got to end the for loop and how do I know the syntax, if you press the menu key, these are all the commands applicable to what we can do here. And you can see if I put that in, the calculator's automatically put the for with the commas. I still need to know what those commas are all about. And you see down here it's put the N for. So if you're using the menus, then you can select the details from the menu if you're not sure what sort of stuff you had in there. Alright, so that's going to produce it 10 times. It's going to display it 10 times, but let's just live with that for the moment because we'll get there. Stored. And now if I run my program, well, there they go. Still a little bit annoying because I'd like to add them up and perhaps find an average. So I could try and do some fancy calculation to do an ongoing average, but that would be a bit messy. So here's where the tricky part comes in, and that is working with a list. Now, the other thing before I work with a list, this is something that I guess goes back to my older programming days. I like to indent stuff that's in a list, in a loop rather, so I can see everything that's in that loop. All those commands are being executed while they're in the loop. And anything that's not indented is outside my loop. So here's the trick that people are probably looking for, and here's where the information can be used later to do some mathematics. I'm going to create a list called distance. And it's really simple to create a list. Oops, need an equal sign. So that's just saying I'm storing a null set, an empty list, in something called distance, or dist, because I can't be bothered typing distance. So how do I store stuff in the list? It'd be nice if I just hit store, but it wouldn't know where to put it in terms of what element in the list am I? Am I first element, second element? So right here, I'm going to get rid of that display because I don't want it anymore. So it would be kind of nice if we could just say distance plus and then put in the next value D. But that doesn't work because this is a list and this is a single value. So there's a special command called augment. And what that allows us to do is connect two lists together. So I can actually get my first, or 3 or 4, whatever you might want to do. So I'm going to put my first list in there, which the first time through my loop is empty. And there's the trick. You put D inside a list, because D, remember, is a numerical value. I put it in curly brackets, it's now a list. So now, what I've managed to achieve is keep a record of all the values that I just generated. So let's compile that. Control B. Oh, and if I want to see it, I best put it down here. Display dist. I'm not going to bother typing any text in there because we're going to get rid of that soon as well. Now when I run my program, how long? There's all the values. So I could do something like this. Mean distance. Well, we said it was probably going to be somewhere between 0.5 and 0.7, 0.707. That's not bad. We could do it again. And I'll go back and get this command. Now it makes sense to put that command in my program, doesn't it? Display the mean distance. So I'm going to come back in here, and rather than displaying that, I'm going to display mean distance. That makes more sense. Now I'm getting more, because the whole idea of a program is to do those repetitive commands for us. So there it is. Now sometimes I get 0.42. That doesn't mean that it's wrong. It just means that I've got a lot of shorter points there. Now, it would be kind of cool if I could change how many times I went through the loop. At the moment I've set 10. That's just because I'm a programmer and that's what I set. You can request it. So for example, and I'm going to use a menu this time so people can see where these things are coming from. Input. I'm going to request, not a string, but just some values. So, and I'll put some text to help us find out what we're requesting. How many trials? And I haven't used n yet, so I'm going to call it n. How many trials? N. And I can put an n here. Let's see what that's done to the program. How many trials? Let's go for 100. That was 100 trials just done. There's another 100 trials. Another 100 trials. So I think it'd be fair to say that this is more accurate now, or sorry, a better estimate of what the average would be. So, where else could I use this? On our website, it's actually an activity for Year 9 students. Here it is here. Tell them what's going on each page. There's a little simulation, little visual for them. So they can use that to do a couple of them, but you wouldn't want to do that 100 times and calculate the average. And then the students do it manually using Pythagoras' theorem. That's why we've thrown it into Year 9. But what if I wanted to do something like this at perhaps Year 11 or 12? It's reeking of sampling distributions here, and it's a good example of sampling distributions because these are truly random events, unlike our selecting items that may be biased in some way. So averaging the age of the students in the class is a biased sample. This is genuinely random. So I'm going to add 2 more things to the program. I'm going to request how many samples, and I'll call that S. And I'm going to start another for loop. Now the disadvantage if you're using the menu, if I put a control here, if I put a for loop in now, it puts the N4 down here. It doesn't know where you want to put it, so it just puts it there. So that's why I tend to type stuff when I'm doing it. So we'll go from 1. Oops, I need a counter. I haven't used M. You've always got to remember all the values using here. And we'll go from 1 to S. That will make more sense in a minute. and I'm going to come all the way down the bottom and 4 right there. So that's the top 4, and you can see why I like to indent stuff here. And I'm actually going to get rid of that display because you don't want to be seeing that 100 times. So what we're doing here is we can take 100 samples and would see the average distance thrown up every single time. We don't want to do that. So I'm going to call something called SAMP. That's going to be my other list. It's a list of samples, and it starts off empty. So now let's run through the logic. So we empty our list because it would have data from the previous sample. And all we're doing is that little routine however many times the user requested. And once we've done, we want to grab the average of those values. Let's just call it mean distance. So we've stored the average of those however many trials, and then we want to record that as a sample. I think I called it SAMP, assigned equal to. So it's a little bit repetitive, and we'll drop in our latest, average. And all this will make sense in just a moment. Display SAMP. Save it. And hopefully I've programmed that correctly. Here's my list, my program. How many trials would you like to do? So let's say they're trials of 100. How many samples of 100 trials would you like to do? Let's go for 50. So it's going to go through 50 times of 100 samples. I left a display command in there, shame on me, and it's finished. Now here's the cool bit. What has that got to do? What sort of distribution, any ideas on what sort of distribution we're starting to form there, Brian?
Looks a little bit normal to me.
Oh, I wonder if we could make it more normal. So,
more normal.
That's right.
Less unusual?
Yeah. So, I'm going to get rid of this display sample. I'm going to cut it out of there, and common sense would say only display that when you're finished. There we go. So, I'll run the program again. How many trials? Well, 100 trials. So in other words, we'll do 100 simulations of our placing points. And let's do 200. This could take a little while. There it goes. Ooh, you might be right, Brian. It is looking a little bit normal, isn't it? Now, we can also see that the mean seems to be about 0.52, which is pretty accurate. In fact, if we change the plot properties, the plot type to a histogram, then that's not too bad for a normal distribution. Now, what I really like about this problem is you can start this at year 9, obviously not with the calculus. Calculus is a university level here, but we can see a standard deviation happening here, and you can experiment with the number of trials, but also the number of samples. Now, all the number of samples does is give us a nicer curve here, but if I change the size of each trial, if I changed it to, say, 400, then that means, pardon the pun, that our distribution, the standard deviation of our distribution, actually becomes somewhat narrower. Because each mean, I'm not likely to get a mean all the way out here if I'm doing 400 trials. Let's just quickly see what happens. I'll do
Peter,
some...
just before you leave that screen, just had a question pop up, someone asking how you got the normal PDF there.
Oh, okay, yep. That was probably a mistake doing that many. Never do that live, right? It's going to take a little bit of time. Oh, there we go.
There it is. Yeah.
Yeah, so let me just get rid of that normal distribution there. Oops. Go away. So, let me just zoom fit.
So our dot plot was changed to a
yes, that's the important step. So let me just change that back. So if I change the plot type back to a dot plot, quite normal. Now, it would be more normal if I'd taken more samples, but the difference here is in the width of this distribution. I think when people saw it, they would have noticed it's a lot narrower because my samples were bigger, and there was 400 trials in these samples. So to answer the viewer's question, so change to a histogram, and then under the Analyze menu, show normal PDF, and in fact, look at that, 0.01. Now before, if you noticed, if you replay this, it was about 0.02 something. So it's halved. That's interesting because I increased the sample size by a factor of 4. And of course that means we reduce the standard deviation by 1 on root n, so by 1/2. And that's about right. We're about half the standard deviation is what we had before. That's pretty cool. Put it into Year 12 maths.
How well empirical matches the theory.
It is, it is. And now I'm also looking at the time, and I know Jim's got a lot to get through. So that's all from me for how long, but you can certainly check that activity out on our website. The activity on the website is focused on Pythagoras' theorem, but people can code it and do all those samples if they want to do it at a different level. So,
terrific.
Pass over to Jim.
Yeah, thanks there, Peter. And I think that was just beautifully developed. Just while I'm handing over to Jim there, I've just opened a poll, and I'm hoping that will come up on people's screens. I'm just interested in knowing how much people have looked already, or may not have looked at the 10 minutes of code. And I see some results coming in now. Thank you. We're seeing your screen. That poll is still running.
Me at dinner time there, Jim. When did you get that photo?
Yeah. Oh, well. So that was actually a great introduction to my little activity because I think I can get out of this very, very quickly and just give you a little bit of explanation and then say, to code this, just shove this little bit in the middle of what Peter did and we'll end up with a similar sort of thing but for an entirely different problem. And that's one of the things that I think you'll see with coding, where we're actually trying to get our students to think along the lines of coding and recognise, well, to solve this problem, I just do what I did in the one we did last week or whatever, because it's essentially the same problem. So hopefully we can give you a little bit of a look at that today. Now, before we get into the program and the code that we've got here, I'm just going to swap to a PowerPoint. Now, my PowerPoint is nowhere near as sophisticated as Peter's, and I just realised I've been playing while Peter's been going on in the background, and had it sitting at the end rather than at the start. But anyway, with the greedy pig simulation, now it would be really great here if we could get some feedback, and I'm just wondering how we can do this, probably in the chat window. Would you just send us a message if anybody here hasn't played Greedy Pig or doesn't know what I'm talking about when I say the Greedy Pig game? So if there's anybody out there that's totally in the dark about Greedy Pig, just send us a little chat message and we will spend a little bit more time on the explanation than we're going to. The other thing about Greedy Pig, of course, is if you have played it, there's all sorts of different versions out there. So I am going to spend some time going through the rules as I've played it with students I've been working with. So here's my rules for greedy pig, and I'll just put this up on full screen so you can see it. So normally we play greedy pig with a standard six-sided die. Now, one of the things I've found in my current job where I'm travelling around visiting schools and spending time in classrooms working with teachers, I've seen a few in the last couple of years play greedy pig. And it is a fun activity, but unfortunately a lot of teachers treat it as just that, as a little bit of a fun activity. And quite often it's something, you know, in the last 5 minutes of a lesson where we're filling time and kids will encourage to tell us, play greedy pig and so forth. And it's unfortunately that they do that because it's such a rich mathematical activity. So this all came out of working with students, doing this activity, playing it with real dice, and then wanting to take it further. So here's the rules as we see it. I don't think there's anybody put a message up there, Brian. I can't see any that...
I got a couple of yes and a couple of no, so it's fairly evenly split, Jim.
Well,
and I've got someone who just said they're hungry.
Oh, righto. So normally if you're playing in a class, traditionally everybody stands and you start rolling the die. Each round consists of 2 or more rolls of the die, and I play the rules. You could choose to leave this out or not. First 2 rolls are free. There's no penalty. And the scores on the die are added to your total regardless of the value. Okay, so a little bit of classroom management. Why do we have the first 2 rolls free? Because then every kid is involved. We all know that if you play an activity, there's going to be some students that opt out at the first opportunity. Well, with this version, the first opportunity to opt out is after two rolls of the dice, which means those students have a score regardless, and we can call on them to ask them to justify their decision. Why did you jump out at that particular score? So it's important to have that in there. After the first 2 rolls, it's then a student's decision whether to remain standing for further rolls of the dice or, as it says there, to stick on that score, in which case they sit down and their round total is the sum of all the dice that have been rolled so far. And the rules go on, because the only other thing that we really do in there is we add a penalty. Now, you can choose any value you like to be the sort of evil number that wipes everybody out. And in our simulation, when we did it with kids, they decided it was going to be at 2. Whatever that is, I actually worked with a teacher, and he had his class going, and they were fairly... they were upper primary school kids, and in 5 minutes he managed to convince them that 4 was the hardest number to get, then 6 was the hardest number to get, and then finally convinced them that 2 was the hardest number to get. So it showed a distinct lack of understanding about probability from that group of kids, but they were just starting. So we decided 2. So if a 2 comes up, your score is wiped out, irrespective of what it is, and you get a 0. And so the goal is to get the highest possible total and stick on that total and not get wiped out with a 2. If a 2 turns up on the first 2 rolls of the dice, you just add it to your total. Remember, the first 2 rolls are free. And a game of Greedy Pig, we make it consist of 5 rounds. And the winner is the person with the highest combined total for the 5 rounds. So that's the game. And the reason we use 5 rounds, that builds in more variability into our result, and more importantly for this simulation, it gives the student time to get used to the game, and then usually by the time they've played 5 rounds, they're starting to think of a strategy. And a bit of a classroom discussion can get 4 or 5 different strategies that the kids are using. It might be things like, oh, go till I get 30. If I get to 30, I'll sit down unless I get wiped out. or some kids might have higher totals, others might be very conservative. Other kids will say, I'll go for 5 rolls of the dice or 7 rolls of the dice or whatever. And that's the one we're going to investigate tonight. That your strategy is, regardless of the total, you're going to stick after a certain number of rolls of the die. So that's our game. So the first thing we have to do is come up with a bit of code to play the game. And what's happened here? There we go. Oh, a couple of examples first for anybody perhaps not quite sure. So if a student, if these were the dice values that were rolled, a 1, 3, 4, 4, 1, 5, they get a total of 18. If a 2 comes up here, remember first 2 rolls are free, so that would be a total of 17. And this comes up, even though they've got all this, 2 comes up, they're still standing, total of 0. So that's what we're trying to do, and we're trying to write some code to do that. Now, as I said...
the greedy. Yep. Jim, sorry to interrupt. I just thought I'd give you some feedback there. Running a poll there. People are saying in the chat that those that have played the game really like it. Think it's quite rich and a lot of good mathematics in it. But about half of the people who've responded to the poll have not played that game. So if nothing else, you've given them a great activity to use with their classes.
They've been deprived, and their kids have been deprived. But it's most important that
good game it is. I've used it with my students.
Yeah. Okay. So now, my flowcharts are not as elegant as Peter, and I'll talk about those as we go through. So we've got 4 little versions of this code here. So the first part is simply to play the game using the rules from the previous slide. And so we can go through those rules and elicit all the information that we need, and we come up with something like this. Okay? Now, going back to my early days of computing, way back, too far back to remember, flowcharting was a big part of that, and I would have been shocked for a flowchart like that because it's got bits sticking out the side and so forth, and we would have been told your program is one line after the other, so you've got to make your flowchart look like that. But we came up with this for the kids. We've got to set up some initial conditions. We've got to deal with our 2 free rolls. We've got to make a decision whether to stick or roll the dice again. And then when we roll the dice, decide if it's a 2, well, we've been a greedy pig and we're wiped out. If it's not a 2, we're going to update our total and do it all again. So I think you'll agree that that's a pretty good flowchart representation of what we have to do in the game and the rules. So let's look at a little bit of the code to do that. So in this file, the greedy pig simulation, we've got a little bit of explanation and say exactly that. And then we go into this one where we simply run this program. And if we run the program, greedy pig 1, the first 2 rolls are free, and I put a little bit of a pause in there so the kids can see the score. So after 2 rolls, the second roll was a 6, and we've got a total of 12. So we decide we're either going to enter 1 to roll the dice or 2 to stick, and I'm going to roll it once more to do that. And we've now got a score of 13, and so I'm going to roll it again. And this is guaranteed this will be one when we go forever and there'll be no 2s turn up. Yep, I'm on a winner here, no 2s, we've wiped them off the dice. Yep, guaranteed to happen in the demonstration. Okay, well, I'm going to change that to 2 and 6. Okay, so you can do that, and the code for this is there. There's a little bit of initializing. We have to set our total to 0 and our counters to 0. First two rolls are free, so we've got a little bit of loop there. It's only 2, but notice here, Peter talked about generating random numbers between 0 and 1. Well, I've used the command for a random integer to get numbers between 1 and 6 to simulate a die. And I'm going to have to move that poll again, Brian, because it keeps popping up where I want to grab things with my mouse. Get rid of that.
That's turning up on the top right, is it? Yep.
Yeah. And yeah, there's the display command to get some information there. Now, we wrote this with kids, so it's a little bit of what we call spaghetti. I call spaghetti code because it's a bit all over the place as the kids' logic came into it, and it could be refined, but this is what I'm trying to show, how we refine this with kids. So now we've got our request to either roll the dice or to stick, and we've got our decision, and the kids just put in a go-to statement to go back to that label and repeat that. Now, we could have got more sophisticated to do that, but that, with the group of kids we were working with, they could follow that logic. And notice we've got the extra condition down here that if they choose to roll again, then if it's a 2, our total goes to 0. We show that the dice showed a 2, call them a greedy pig, and we again go back up there and repeat it, and here's what we do if it's not a 2. So as Peter showed you in the last one, sometimes coding is a little bit repetitive as we deal with the different conditions and so forth, but that works. It lets us play a game of greedy pig. Now, if nothing else, that would be a good starting point for another little thing. It's not what we're going to get into here, but I did do a little bit of a creation with the TI Innovator and a breadboard and a whole pile of LEDs, and tried to hook that up and make an electronic dice to play that game. And we'll get there, but I got too many bits of wire going everywhere that I didn't quite finish it, and then went back to it and lost track. So that's the program for another day, to hook up Innovator to make our, instead of just saying it came up with a 2, to get our electronic dice to display a 2. So moving on, what's the next part that we're going to do with this? Let's go back, where did I get to there? And their refinement is, then we're going to play a complete game. So play 5 rounds. Can you see the parallels with the activity that Peter had? He was going to repeat that for a certain number of trials, and then you'll see what happens as we go on. We're going to repeat it for a certain number of games as well. So we repeat it 5 times, 5 rounds for a game. And to do that, then we no longer need the stick or roll prompt. We're going to replace that with a loop. And a little bit like what Peter did, we're going to add the scores together to get the game total. So if we have a look at the code for that, we've got our 2 free rolls again, and then my strategy here was that I was going to repeat this 5 times, and we introduce a counter rather than the, actually I might have made a mistake there, I've confused myself. Yeah, we're good. But we're repeating that entire program 5 times to get some results. So let's have a look at the code for that, and you'll see better what we mean. So we're going to go through to the second one. So this one plays 1 round of the game using the strategy you decide. And the strategy simply to decide how many rolls of the dice you wish to play every round. So easier to run it and show you what's going on. So we're prompted for the strategy, stop after how many rolls. Just to change it, I'm going to put 6 in there. Okay, and so in this case, we were going to sit it out or stand up for 6 rolls, but after the 4th one, we got a 2, so we've got a total of 0. And you can see that if I keep that strategy, this time 16, this time another 0, and so on. So you get the idea that we've now made the code give us one complete game, or one complete round, rather, I'm getting myself confused, one round of 6 rolls of the die. Okay, so there we go. We got wiped out in the last one there. So in order to progress through this a little bit and look at what's going on at the end, I might just stick with what we've got here. In the program Greedy Pig 3, we'll build a complete game. And so we take what we had there, 5 rounds, 1 round, and repeat it 5 times. So we get the complete game. So there's the code, and we go in and run it so that you can see from that example there. Let's just change it. Let's do 7 rolls, and how many trials? We're going to do, let's just do 2, and you can see that in this game we got a total for our 5 rounds. Remember, one game of Greedy Pig is 5 rounds, so we got totals there that gave us a game total of 115, and I said do it twice, so there was the first one. Now, what this does with kids, if we run it again, and run that there, we'll do 7 again, and let's do 5, okay, we'll see. And you can see what happened there, that with 5 games, then it gets a bit tedious scrolling back, looking at all the results and so on. And in actual fact, that code, if you were to put in 50 games, it would do 50 games, because the kids have got nothing in there to stop it. They just decided that, oh, that's too many. We will just tell people to do 5 or less. So it's a long way to go for their programming, and if you want to play around with this, there's a lot of refinements that you can make. But we've built that up now that we can go from playing 1 round of Greedy Pig to a complete game of 5 rounds, and now we can repeat the games based on these strategies. And so then we go, much like Peter did, that Peter was wiping out the display statement, and that's exactly what we've done here to get to the final version, that we don't want to see all of this. We just want to get the game total. And we don't just want 3 or 4 or 5. We want lots of them, which means we're going to have to store them. And so that's our final version, and it says up to 1,000 games. Now, when you look at this, I actually learnt something from Peter tonight watching him do that, because I didn't know you could just define a list being null at the start, and that would wipe everything out. And so our kids, we wrote a little loop to make sure that if they had 1,000, up to 1,000 it says, so they wrote a little loop that goes through 1,000 times to make sure that every element in the list is a null value, so that in case they did, say, 500 games and then repeated it and said 200 games, well, those other 300 values would still be in the list. So we both achieved the same result, but Peter's is a little bit more sophisticated. And you can compare the 2 programs when you do that. So when we run this, in a sense, it's a lot less fun, a lot less spectacular, because we're going to run Greedy Pig 4, and it'll say stop after, or let's say 6 rolls, because that's what's there. And how many trials? Well, let's do 1,000, and it's finished. And in the same way that Peter did, we were putting those values into a list, and I went to the extra step and put those lists into the spreadsheet so that the kids could actually see it and verify what was getting there. So it's a little bit long-winded, but it was important going through it with the kids to build the code progressively so that they knew what this number was. This was the total from 5 games, and the code was actually doing what they did right back at the first version of the program and playing the game. We just added the strategy so that it played the game automatically. And of course, the beauty about the nspire, once you've got this in there, exactly the same as what Peter did, we've got all these tools built in, like the data and statistics window that allows you to display this data in all sorts of different ways. And the task we give the kids then is to decide what is the strategy that you would use. Are you going to stick on
Jim?
Yeah.
And I know this is a question without notice. One of your favourite things to happen right in the middle of a webinar, right? But you're used to me doing this, so that's fine. Can you do me a favour? Can you go back to your calculator page where you've got...
Which one?
Where you're running it? Yeah, that's the one. Click on there. And let's just call it, I don't know whether you want to call it T2, something like that. Do T2 is assigned equal to total.
T2.
And yeah, is going to become equal to total. That's it. Press enter. Now, yep, press enter, and that will store a copy of all of those results. Now, you can probably figure out where I'm heading now. Can you run the Greedy Pig 4 simulation again, and let's stop after 5 trials.
Okay.
So if we stop the 5 trials, what I'm looking for, particularly since you've done that beautiful box plot there, is 5 trials a better strategy than 6. And while he's doing that, Brian, see if, and another one, without notice, I don't know whether you can do it that quickly, is set up a quick poll on the chat to see who thinks 5 is a better strategy before Jim graphs it. If 5 is a better strategy than 6, so whether we want to stop after 6 rolls or should we stop after 5 rolls. Bearing in mind, Jim's done 1,000 trials in this, so I think we should be reasonably confident that the data that he's generating would be an accurate reflection of the true probabilities.
Because I know my strategy for the game is actually based on something different.
Oh, okay.
Not actually the number of rolls. Yeah, no, it's not. Not actually stopping on after a number. Yeah.
So Jim, if you go onto your box plot now on that stats page, you should be able to add an X variable. So you can see it's automatically updated your data that you had before. Now down the bottom, you want to add another X variable.
Sorry, right on, yeah.
On your axis, yep. And T2. So T2 was, what was our 6, wasn't it?
You are a little Vegemite, aren't you? Yeah.
Yeah. Sorry, I'm just leaping ahead here because I can see where this is going, and I think it's really cool. Well, actually, there's not a massive difference, is there? I think the median is up for 5, but, gee, that's a really tough call, isn't it?
It's a popular vote is
one of the big things, this was the one with 6 rolls, and of course the more rolls you decide to stick it out for, the more chance you've got of getting a 0, and that drags things down.
Yeah, but look at the standard deviation, look at the spread of the data, and of course I guess we'd expect that because you're potentially reaching higher scores, so it's a good way of actually understanding what that box plot's telling you, isn't it? There's a lot in there. Yeah.
Greedy Pig.
There's a little part of me now, Jim wants to go T3 and run this whole thing again, but we'll run out of time. So that's something for our participants to do, yeah?
Yeah, and look, there's lots you can follow up on here, and if I can just finish off by jumping back to the PowerPoint and going through to the end, because one of the things that we came up with is, yes, you can vary the rules of the game. So you might like to you know, get rid of the first two rolls of 3, or you might like to use 2 dice and add the total, but you wipe out if it shows a double, which is another version that people play. And so there you've got obviously 2 dice and all sorts of different probabilities coming in there. I found this one really intriguing. Vary the dice so the 2 dice are not identical. For example, you had a 1, 2, 2, 3, 3, 4,
ouch.
and something like that. Then that becomes it becomes a lot more difficult to code, because you can't just say a random number between 1 and 6, because we've got to somehow weight these probabilities and so on. There are ways and means around that, just by linking it to another variable where the values are stored. We've still got a 6-sided die. But it's an investigation that you can play around with and see, and especially if 2 is the evil number that wipes you out, then that's only appearing on 1 dice, so what does that mean, and so forth, right? And then I think this is what Brian was alluding to before: stop when the total reaches a certain value, and you can change the looping controls and that. And as I said, start playing with Innovator and build an electronic die to go with the whole greedy pig thing. So that's where I got to with that one. It's been an interesting investigation to build the code with kids, as I said. So some of that code in there is exactly as we built it with the students, so it can be enhanced and be made more efficient, but that's the way the kids' minds were working, and it worked, and it showed that, you know, they could follow the logic through with that. And I think that's the starting point. Once they understand what it's doing, then you can start to refine it. I probably
That's really good.
longer, Peter, but yeah.
Can I get you to go back to that box plot? Because I think that box plot's pretty cool.
Intrigued.
I am. It's the first time I've had a look at the 2 sets of data, because I know you said this strategy, and I thought, I'm going to wait until tonight to see this, because I wonder if students that chose T2 and said, I think 6, holding on for 6 is a better option, perhaps the more or greater risk takers, they're seeing that the potential to get a big score outweighs the fact that on average they'll end up worse off.
Yeah.
Mm.
Yeah.
But it depends also on the psychology of who you're playing against. You've got to try and second guess your opponents and think, how greedy are they? Basically, no guts, no glory. You've got to go for it to win the game.
So you're at T2 then, Brian.
You'll see that in class when you play it with kids, that when you've got them standing up, you'll pick the one that is standing up, and he doesn't care what the scores are. He is going to be the last man standing, and he will wait it out regardless.
He's there to win.
If you get one of those and you get a run like I was having on the dice before, where 2 seems to have disappeared, it can be a long time in a classroom going through with those when you've only got 1 or 2 kids standing. Yeah.
Yep, and of course I expect you see my strategy, because my strategy is actually based upon the cumulative total, because that is what changes. It's how much you're wagering. The probabilities, of course, or the expectation of what will come up on the roll of the die, that is a constant, and it can be calculated. But what changes as you go along is how much you're wagering against that expectation. That's my answer. That's what I did with my methods class anyway.
So one of the things, one of the challenges almost I wanted to put out there is if people want to, you know, take this up and run with it with a class and make some changes to the code and create some other versions such as those strategies you've been talking about, they might like to share it and perhaps send it into Peter at the office there, and we might feature some of those in a future Problems Worth Coding one, just a little bit of backtrack to this one and see where it's got to. So those of you out there, become a bit of a participant in the webinar and send us some information.
Yeah, well, this will be up on the website hopefully by tomorrow afternoon for people to download, Jim, so good idea.
Yeah. Well, Jim, I'm just seizing the show back there.
Good. Yep.
And So thank you very much for that, and a terrific problem. I reckon that's it's one that quite a lot of us have used, and in the polling, quite a few people hadn't. So they've got some value on a great game there as well. Thank you to both of our presenters this evening, both Jim and Peter. And Peter started us off with coding through the problem there, which I think was beautifully developed bit by bit. Well, the first time we ran his program, and it apparently didn't do anything. Just how long it executed, and it wasn't until we looked to see what was happening in the variable list that some variables were written in there. And I thought that was a terrific progressive development there, Peter, for people who are just looking to add greater levels of complexity to their coding. Interestingly enough, when we did the poll, only about half of our group have actually used the 10 minutes of code. I will show people at the end, just before we go, I'll show them how to access that once again, because that is what I think is an ideal starting point for both teachers and students. So thank you, Peter. Thank you also, Jim, for a revisit to a problem that I have got a lot of mileage out of over the years. In the chat window, you're getting people hungry. There's a lot of references to bacon sandwiches and and the like. I was pleased to see the flow chart in there, which is, as you said, when we started out decades ago with our coding, the flow charts for the algorithms were absolutely critical, and I think that's still an important thing to include. I really like your extensions with the game, with changing the numbers on the die, which of course would change the expectations and really opens up some wonderful investigations. I would really like to see the Innovator Hub with the lights and buttons game extension on that. I think that looks fantastic. If nothing else, I can tell you I'm going to steal your coding and use that next time I play that game. So we'll close off the webinar shortly. Participants, when the webinar closes, you'll be taken to a page where you're invited to provide us some feedback. Please write all sorts of wonderful things in there, because I think your presenters are well worth it. And within a day or two, you will get a follow-up email including some of those codes as TNS files. You also get a PD certificate, and I know you participated strongly because I saw it in the polling. If you want to view this again, you can do so via the TI website, but also a lot of these are now appearing on our YouTube channel. There's a great wealth of video there for you to view, and I think it's also something that's good to view with students, even if you just choose to view short sections of it. There's the address there on your page. Now, your number one page, of course, is the Texas Instruments website. If you type in education.ti.com, it will take you by default to the American TI site. See here, SITE. If you click on that, you have the option to change which site around the world will be your page. I have by default set mine to Australia and New Zealand, and alternatively you can just Google TI Australia and New Zealand and it will take you to this on the first hit. From this front page, here is where you go into the webinars. I expect you've already discovered that, but this one here, this is the link through to the 10 minutes of code. So clicking on that, sorry, I'm just on a PowerPoint here, but clicking on that will take you through, and you can do the coding either on TI-nspire or also on the TI-84CE. It's step-by-step activities. It's something that you can easily just direct your students to, and they will have more than 10 minutes, much more than 10 minutes of enjoyment there. If you don't have the latest operating system, which was demonstrated there, you can download here at operating system 4.4. If you enjoyed this evening's webinar and you would like to see more, we have another one coming up tomorrow evening, particularly focusing on further maths for Victoria and applications Western Australia, and we have a presenter from each of those states. And next week, if you've particularly liked the coding, you might like to take it to the next level with STEM, and we have STEM next Tuesday evening with the TI-nspire and STEM on the Wednesday evening with the TI-84.
Thursday, Brian?
Yes, so...
yeah.
Oh, sorry, Thursday. Thursday, that is. It was to be a Wednesday. We've postponed it to Thursday. Thank you, Jim. So that's it from me, and good evening from the presenters.
Thank you, Brian.
Thanks, Brian.
Thank you both, and all the very best. Good